Alright, hell yeah. So I had an aha moment. So we're doing differential equations. And typically what you can do is, if you have a position vector, I'm already confusing the hell out of people, but if you differentiate with respect to time, you get a velocity vector. Alright, hell yeah. But a lot of things you'll have to use like the chain rule, and you'll have to take something and then differentiate it with respect to x, and then do a dx dt. But anyway, I just wanted to know, if I take a position vector and differentiate with respect to x, like what the hell does that even mean? I've always wondered that. Just every time I get a new problem, I'm going to try to do that to see, like, well, what does that mean? So with this problem, we have b is the position, and as this stick rolls up into a vertical, see, you can see how b goes this way and that way. And if we're talking Cartesian coordinates, the x, y, we can see that, hey, at some time b is going to be over here, and it's gonna follow maybe like this path or something. And so it's going to have a position this way. It means it's going to have some velocity this way. It's going to have some velocity that way. At this point, it's going to start to have some velocity that way. At no point does it ever have velocity downward, but you can. But any changes in the velocity vectors, is going to be acceleration. We're not going to cover acceleration in this, but we just kind of wanted to know what this differentiating with respect to x. So when I took this position and differentiated with respect to time, hell yeah, I kind of I know that this velocity is like 2 feet per second, and I know that Alright, hell yeah. So I had my first aha moment. When we're differentiating, a lot of times you want to get a position vector, and then you're going to differentiate with respect to time. And that's going to turn whatever position vector you had into a velocity vector. And you're going to get a whole equation for velocity. You're going to be like, hell yeah, I know the velocity, of this point as this stick goes up like here. Hey, I know the velocity is going this way, and then I know the velocity is going that way. So you can kind of see this stick. And so that's differentiating with respect to time. That's always visual and understandable. But I was always curious of like, hey, what does it mean to differentiate with respect to x? Because this comes up a lot when you're using chain rule. You'll have to do like differentiate with respect to like x, and then dx dt to have kind of two separate products there. Anyway, so this problem was kind of interesting. Like for the life of me, it took a long time to set up, but we finally got it. So this is going to be my x is equal to 0, and if this is 2 feet, this is about 3.5 feet. And so we're going to have like, let's do it. 1, 2, 3, and then just a little bit more. So hell yeah. So this is going to be 1 foot, 2 foot, 3 foot, and then you got 3.5. Okay, so now what I want to know is when x goes from 0 to 1, what does this differential, like what is differentiating with respect to x? If I have my position vector and I differentiate with respect to x, well, we're going to, and you have to do this in smaller bites, but we can just say, hey, let's say x goes from 0 to 1 feet, and this b, because if we look at this, what's going to happen here, we're going to come up like this, and that's going to be the path of b. Well, hey, b only goes like 0.74 feet. So if we take this thing up to here, hey, this went a full 1 foot. But if we come over here and say like, oh, no, this just went like 0.75 feet. Okay, hell yeah, or 0.74. So now we have a visual representation of what differentiating the position vector with respect to x. It's a percentage. It's like, hey, if I move this like 100%, I'm only moving this point 74% in this direction. All right, hell yeah. And then if we get the position vector in the vertical direction, so we're going to move this 1 foot, so we're going to go like up to here. And so maybe we only got to, maybe this point only traveled just like right up to here. So we have 0.74 feet this way, but then here, hey, maybe that's just like 0.43 feet. So hell yeah, with an incremental change, or if we change this like 100%, this only changes 43%. Alright, hell yeah, I gotta jump in here because this is something you can always do and I don't do enough of, because we were saying, hey, this moved over 0.74 feet, and then it moved up 0.43 feet. And then we moved an increment of 1 foot here. Great. These are in the x direction and y direction. And so get into the habit of being like, hey, let's take the square of both of these, add them, and then take the square root, because that's Pythagorean's theorem. So we have 0.74 feet, 0.43 feet, and we're going to square this. Sorry for the scribbliness, but hell yes, we're going to have the square root of 0.74 squared plus 0.443 squared. And for sure, so we get this b goes in this direction, kind of the linear, the vector direction, the linear direction of 0.855, so 86%. So if we have a 100% incremental change from 0 to 1 foot, this only goes 86%, and it's these two components that we're looking at. All right, hell yeah. And I think if you think about it as a percentage, it kind of gives you a more visual representation of what's going on. Hell yeah. Alright, we're going to finish this video also with a little bit of trigonometry. So I was able to take this problem and set it up in derivative calculator. You know what I mean? So definitely support them. Go and check them out. Just a really useful tool. And so one thing that I'm going to point out is, like, man, I never knew this is so classic and it comes up, so much. Like, if we want to know, like, let's say this is our origin, like 0, 0. So we have and we're going to start here, x, and then y. And I want to know where this position is located. Well, this is going to be 4 feet. So I'm going to go over about 3.5 feet, and then up 2 feet. So if I had to write that as a position vector, I would say 3.5 in this I direction. Now the x direction is the I hat, the y direction is the j hat. The z direction out of the page is the k hat. Hell yeah. Alright, so I'm going to have a position vector. I'm going to go this way, 3.5, and then up 2. So we're going to go up 2. Okay, and then who knew that if you just have an angle, and you're always, so the take-home point, I guess, is if you're always taking your angle from a horizontal, hell yeah, it's always going to be like, hey, you're going to take this 4 feet, multiply it by the cosine of this angle to get this distance. And then you're going to take that 4 feet, multiply it with the sine of that angle to get this distance. And I've always mentioned, we're talking about percentages. Hey, this is a percentage of this 4. So if this was a percentage of 4, this is going to be 50%, because that's sine of 30. This angle is 30. Alright, hell yeah. Now, if you want to confuse the hell out of yourself or just make the problem trickier, take your angle from the horizontal. Say like, hey, I'm going to start my angle here. This is going to be 0, and I'm going to sweep it out this direction. And then just call it something different. Call it phi. And if you do this, well, now you're going to be totally opposite. And you might have to figure out where you want it. I've never done this before, actually. So I don't know if you want to take it from this and go this way, or you want to take it from this axis and go all the way around. I imagine you actually want to start here and go all the way around. But anyway, that's kind of not what I was getting at. Alright, that was just a side that, hey, if you do take your angle from a vertical, hey, this sine and this cosine switch places. But most everyone takes an angle from a horizontal, and you're always going to have this representation. You're always going to have like some magnitude, some distance, a percentage due to the cosine in the I hat direction. So here's your x component, y component. X is always cosine, y is always sine, given that angle comes from the horizontal. Alright, hell yeah. And then what I've been working on more is like any time that I can use Pythagorean's theorem, I'm going to do that. So when we get our equations, so right here, this is, so when I set up, so what do we have here? What I'm gonna actually do for this equation, I'm not gonna set my 0 axis here. I want my 0 axis right here. Cool. But then I want to, like this point, I want to use these lengths, you know, to describe this point. So we know this initial setup, it's 30 degrees, it's kind of the initial setup, time 0, let's say x is 0. The cool thing about differentiating with respect to x is I can set x right here. I can have my Cartesian coordinate up here, but if I differentiate with respect to x, it can be a totally different location. Hopefully I'm not messing that up because it's kind of the first time I've been doing this. Alright, hell yeah. And then so if this point B is at 0, so at x is equal to 0 or time is equal to 0, hey, B is basically 0i plus 0j. That's the coordinates on this. Okay, sweet. But if we want to use, but how I set up the equation is like, hey, I'm going to say this point is going to be this initial 4 feet, because when we start to move up here, to, let's say, to this location, let's just draw it in, and B is right here, this distance is still 4 feet, but then what I want to know is actually this distance, you know, this kind of remainder distance. So I'm going to say, and at every time, or every x value, I always know this hypotenuse, I always know this height, and I can always know this, because I know how a right triangle operates. And so, so what I'm going to say, this distance right here, which I'm just going to call like a vector, so if vector b is equal to the magnitude of vector b, this is going to be the magnitude. So I'm just going to say the magnitude of vector b is this distance. And I'm going to say that, well, we don't have to get too crazy, but we're just going to say that's equal to 4 feet, this whole thing, but minus this hypotenuse. Okay, so now we need to figure out what the hypotenuse is. And when we take it from the initial condition, well, the hypotenuse... Alright, let's slow down here, because this is also fascinating. When dealing with right triangles, you know, this is a free angle, you already know it, but it's kind of cool that you only need 2 things to know everything about the triangle. So for this problem, they give us this initial angle is 30, and they give us this height is 2. So then we can use any kind of, we can just go for it to figure out any way possible to figure out what this hypotenuse is. We know that the sine is related. If the sun is shining, it's shining on this side, so this is your sine component. We know that the hypotenuse is bigger, so that's kind of the first thing, is like, hey, and we know sine of an angle, sine of 30, this is always a percentage, and it's a percentage between 0 and 100, so this is always a number less than 1. And if we want to multiply or divide by this, we want to take that percentage and then do something with this 2 to get a bigger number. So what would we do? Would we take 2 times a smaller number, or a percentage, to get a bigger number? Hell no. But we can take this 2 and then divide it by sine 30. Hell yeah. And we can get this hypotenuse. Alright, hell yeah. And then you could do the same thing to get this. You could say, hey, I know my hypotenuse now, and this angle is 30, and I want to know the cosine component. Well, if I already know the bigger number is the hypotenuse, I just need to take a percentage of that, kind of in that cosine direction. So I would take cosine of 30, that's going to be that percentage, and then I'm going to multiply it by the hypotenuse. Hell yeah, and I can get that. But, like, why do that? Anytime that if you have a right triangle, you have 3 sides. Anytime 2 sides present themselves, you can use Pythagorean's theorem. We know that this side squared plus this side squared is the hypotenuse squared. Or you could say the hypotenuse is this squared plus this squared, and then the square root of that. That's kind of how I say it. But if we know the bigger number, the hypotenuse, and just any of the other sides, we know that this remaining side is a smaller number than the hypotenuse. So just the generic formula is, hey, you take the hypotenuse squared minus this side squared, and then square root that. You know what I mean? So it's the hypotenuse squared minus, a side squared, square root that, and that's going to be this other side. You know what I mean? So that's one that you definitely just want to kind of have on lock. Alright, hell yeah. So now let the magic begin, because now we just said that this is the square root of 4 squared minus 2 squared. Square root that. So let's grab a new sheet of paper. Alright, hell yeah. Got a fresh sheet, and we're going to clean this up. So if you know this is 4 and this is 2, this is going to be 4 squared minus 2 squared, square root that. Alright, sweet. And alright, hell yeah. And so this actually comes up in statics. Kind of when you take statics, they want you to do this, and I just didn't want to. Maybe that's why I didn't learn it very well. But anyway, so, because if we come back up to here, we're going to have this magnitude of b, and then the cosine is just going to be this component. Cool, well we already have an equation for that. And then same thing here, we're going to have this magnitude of the hypotenuse, but times a percentage is going to be that. And so what does cosine say? This cosine of the angle, just this term right here, again, it is a percentage. It's a fraction between 0 and 1. And it says it's going to be the adjacent, if here's the angle, sun is shining on the sine, and this is the cosine component, it's going to be the adjacent divided by the hypotenuse. You know what I mean? So we can just write this, we can rewrite this as, and I'm just going to say this is the initial b naught. So we're going to say b naught times, well, we're going to do this divided by that. So we have the 4 squared minus 2 squared divided by 4. And I guess I should just spell this out. This is going to be 16 minus 4 is 12, so we have the square root of 12. Okay, hell yeah. So, and this is going to be in the I hat. Let's do it for this. We have b naught sine theta is going to be the opposite over the hypotenuse. So that's going to be 2 divided by 4. So now you see that we have, you know, kind of this length of 4 feet. 4 feet is b naught. And then this is going to, you know, be 0.866, which is the cosine of, you know, it's the ratio. Even though that these are larger numbers, this is always a percentage of this. So if this is 100 feet, this is going to be 86.6 feet. And same with this. This is going to be 50 feet. It's going to be half of whatever that is. All right, sweet. All right, hell yeah. So now for the problem setup. So for the problem, I just called this H. You know what I mean? I think it's really good that I'm getting better at. You know, just use all numbers to like get to where you want to go, but then go back and redo the problem with just values. So I'm just going to call this the height of that step H. I'm going to call this just B, just capital B, and that's going to be this initial, you know, length. And cool. And this actually never changes, because we're just going up here. This value changes, and I'm going to call, I don't know, I think I start to call this H, but we solve for it in terms of other things. This I'm going to call just length. I think I kind of like that, you know what I mean? Have L down here and then H, so you have length and then height. Okay, so let's grab a fresh sheet of paper. Now if we do move this a distance x, you know, you'll come in here, and then this stick is going to be at a new location. And then if this is B, you know, B would be right here as a function of x. Okay, so hey, this length changed. So what is this new length? Well, it's going to be this original length, L, and then just subtract this x that we're already saying this is x is equal to 0. Maybe this is x is equal to 1. So cool. So and this is obviously 3.5 feet. And so if we subtract 1 feet, yeah, we know this length now. So this is going to be L minus x. I think that's the hardest thing for me to get to. Okay, hell yeah. So now we know this hypotenuse right here. And I'm just going to say, hey, it's h. And I'm trying to get better as like, hey, this is going to be a function of x now. We could have done hypotenuse as a function of time, but again, we're trying to get everything as a function of x and then differentiate with x just to make sure we kind of understand what's happening. And when we read, I mean, the foreshadow is we're going to put them into derivative calculator and then read these graphs. Okay, sweet. But the cool thing about this is we're not going to use the angle. We already know the two sides, see? So I'm trying to use the principles. Hell yeah, I'm trying to develop my own markers when it comes to trigonometry. Like, that's a classic one. Well, I just came up with it today. That was crazy, just even this video. It's like, well, if I have two of these sides, Pythagorean says we know the other side. And it's so important to do that in trigonometry. So hell yeah, now this is going to be pretty simple. It's just going to be, and we're calling this h, so it's just going to be h squared plus L minus x squared, and then square root it. Cool, so now we have that component. And so now when we go up and put in this, well, we have a couple things going on. Oh yeah, I always forget about this. Okay, so this initial length is b. Kind of like, I just call it b naught. But here in derivative calculator, I just call it b. But this is going to be b naught. Alright, so cool. So that's that initial length. When we roll this thing up, that length doesn't really change. This is still b naught. But what I'm curious in is this distance right here. Like, that is what I want this to be. But the way to get that is to, hey, I know this hypotenuse, and then I know this full length. So that's another thing in trigonometry and just geometry that comes up all the time. Is like, hey, always say, okay, that's the length I know. Maybe I know that length, and I know this length. I know this whole thing is 10, and I know that this thing is 8. You know what I mean? Again, these representations come up all the time in problems in trigonometry, and you just need to be like, oh, hell yeah. Kind of like light bulb goes on. I know what this is. It's going to be 10 minus 8, and I know the equation for it. So if I want the equation for this distance, which I'm going to call actually just bx, and then I want the equation actually for this distance, which is by. But even that, like, this is, like saying that and putting those in is more advanced. I would never be able to do that. Like, I just kind of come in here and be like, okay, I know that this is 4, but I know this. Okay, hell yeah. So then I'm going to take this 4 minus whatever the hell this was. Cool. And now that we have them as letters, I'm going to take, so bx now becomes b naught minus this h of x. And I've done this problem 1,000 times, so now I can even write, but I would never write it that way either. I would just say, hey, it's 4 minus, and this is where I just would use numbers, but we have to use letters at some point. And so we're going to say this is h squared plus L minus x squared. Okay, hell yeah, so that is bx. So when I do bx cosine of the angle in the I hat plus by sine of the angle in the j hat, this is my position vector, and this is what we're going to be differentiating. But hell yeah, we at least have the first part. That's the only part we solve for. We just solve for this little direction, and it's a vector. And hell yeah, we have an angle. But this angle is going to be the same. And so now, and I didn't even realize, I just knew to use this triangle, even though I got the length of that thing. So hell yeah. And then again, I think the take-home point is, hey, anytime you see cosine of an angle, it's well, one step farther. It's a percentage. If you see sine and cosine, think percentages between 0 and 1. But if you see tangent of an angle, sine of an angle, and cosine of an angle, think ratio. And so now I'm just getting in the habit of actually just spelling out the word ratio. And we'll do the opposite. If you see inverse tangent of an angle, inverse sine of an angle, inverse cosine of an angle, also called arctan, arcsine, arccosine. Hell yeah, these are angles. And then just spell it out, because I think, for me, what gets confusing is I see tangent of an angle. I don't know, it just screams, the angle is in the name of tangent of the angle. It's It should be tangent ratio. You know what I mean? That would actually be pretty good. If anytime you see this, say sine ratio, cosine ratio. It's not cosine of the angle. The whole thing is called cosine ratio. And it does involve kind of the cosine. So let's go back to cosine. Cosine involves the adjacent and the hypotenuse. And I'm going to double down. The angle with the sun is shining, and it shines right on the sine. I mean, this would have helped me so much in college. This component's always the sine component. Even if your angle is vertical, you want to take your angle from here, you know what I mean? Hell yeah. Sun is shining, this is the sine. And that means that this has to be the cosine. And the hypotenuse, hell yeah, don't mess that up. It's always the bigger number. Alright, hell yeah, we're almost there, you know what I mean? And this was just this is a really good way for me to start the camera. Have an aha moment, print some print-offs, like don't go into the 5-hour problem, just like hit the highlights. So this problem is still kind of complex. You still had to figure out how to get this little chunk, but we did. And it's at this angle, angle's the same. So we're going to take that chunk times the cosine. So back to that, we're going to say ratio. And it's the ratio between this and that. Okay, it's the adjacent over the hypotenuse. Even though you added letters, they look awful, but let's turn the page. Because this is going to be that b minus, this is going to be this, what we're calling b of x. Okay, and then let's look at this. Is this the cosine? Is this the adjacent L minus x divided by the hypotenuse, which we said was h squared plus L minus x squared? You know, so that was the whole point, is like, can I look at this equation and visualize it? Can I see a triangle? And I can see that this is the height. This is my L, but minus x, because we're varying it as x goes from 0 to 3.5. Cool. This part gets smaller. This hypotenuse, this height never changes, and so we have those two. We know what the hypotenuse is. It's going to be h squared plus L minus x squared, square root that. So we know what that term is. This was 4. Then we come in here, this is 4, but we got to go 4 minus that hypotenuse of that triangle. So that's how we get this, 4 minus that hypotenuse, but then we need to multiply it by the cosine of the angle. And like I said, don't call this, I'm going to revolutionize trigonometry. Don't call this cosine of the angle. Call it cosine ratio. Oh man. You know, give a like right now if you're just like, whoa, you're just reinventing mathematics. Sweet. So you have this cosine ratio, and it's the adjacent over the hypotenuse. Is this the adjacent? You know, back to our imaginary triangle. Hell yeah, this was L minus x. And then this was that hypotenuse. And you see the hypotenuse is up there. It's the same. Hell yeah. Now you got everything. But this is the hardest part. To take a problem and set it up correctly. Because then, you know, I took the second derivative. First derivative gives you, well, again, now we got to talk about that. What the hell does it even give you? It gives you the position with respect. So the derivative of this gives you derivative of bx with respect to x. Even just saying that makes absolutely, like, I mean, I get it. That's how you say a derivative. But what we're doing is we're changing. This is so cool. I'm going to change x 100%. Now, how much did this actual point move this direction? You know, and kind of in terms of x. Well, if we come down here, it only moved 75%. So hell yeah, our change in bx was 75%. So we have 100% input. We move this thing like 100%, like one foot, and this thing only moves 0.75. So that's kind of cool. And now from here we can actually read the graph, because I can only throw in one value of x right here. But so we're looking at the red line. So here is 1, here is -1, and alright, hell yeah, and I'll just spell it out for you. Here's where this thing hits vertical. So this thing's going to come up and hit vertical right there. That's going to be that 3.5, 3.45, 3.46 or whatever. So, and when that happens, hey, so check this out. So when we come in here, hey, this component, the new position is here, but obviously that's going to be associated. Oh, damn it! I'm mixing it up. I'm associating this with velocity, and it's not. It's just saying, hey, if I move one increment here, this only moves 75% of an increment. Holy Toledo. But anyway, so let's follow this path. We're going to go here, and then we're going to go up. So if this is 4, I'm just going to go 2, 4. So this thing gets up here, and so here's the path that B travels. And so what you'll find is that at some point, right about here, when we do a small increment from here to here, look, hey, B did not travel in the x direction, or the I hat direction. It traveled 0. So if we go back to our graph, hell yeah, right here through here, this is 0. You know what I mean? Kind of a 0 value. But right at the end, it's 1. You know, so what does that mean? And so when we take this whole thing vertical, just right before it gets to be vertical, check this out. Now let's just pretend that this is 1 meter. 1 foot, since we're working in feet. And I'm going to move this 1 foot. Well, how far did this move? Hey, look, it almost looks like it's at a pivot. And, you know, this thing does, as long as this isn't in the total vertical position, this basically theoretically acts as a pivot, even though when you do push it in, this point at the pivot moves slightly up. But hell yeah, so you can see with a 1 foot input here, you get a 1 foot output there, and it's in the negative direction. So if this was our coordinate system, so we have x or I hat, and this is going to be positive x, positive I hat. And then this is going to be negative I hat, negative x. This direction. This is going to be positive j, positive y. Hell yeah. So now you can see that's going to be in the negative I hat. And so that's what we see. It's a negative 1. So we have negative 1 for that. All right, hell yeah. So let's do the same thing with this. So we have b sine theta. What should we see on the other side of the page? We should see that initial length b minus whatever this was. It was the hypotenuse, square root h squared, plus, you know, these two sides squared. You know what I mean? Square root that. And then, so that's going to be this representative hypotenuse, but we just want this side of it. So that's going to be part of the sine. So we want the percentage. So we have sine of the angle, and we can think the sine ratio is going to be the opposite over the hypotenuse. And those two numbers are going to give me a fraction between 0 and 1, or a percentage between 0 and 100%. Sweet. In this case, it's going to be 50, but we're using letters, so that ratio is going to be h divided by the hypotenuse. H divided by the square root of h squared plus L minus x squared. So let's go over here. This is going to represent by. This whole thing represents by. So by j hat, and by in the j hat direction is the initial length of 4 feet, b, minus, so let's do our imaginary triangle. We're going to have 4, but then we're going to, when this thing rolls into here, we're going to have minus this hypotenuse, which was this side, h squared, plus this L minus x squared. Cool, I'll square root that. So that's going to give us that little hypotenuse. And then we got to multiply it by the sine of the angle. That's the sine ratio. So that's going to be the opposite over the hypotenuse. That's going to be h divided by that hypotenuse again. So hell yeah. So and then there you go. So that's using all letters, and it's pretty cool. So what this showed was that at right at the initial, hey, this was going to go like a 1 incremental change in x. Hey, this sine, so we go from here to here. Hey, this sine only goes up to 0.45, 0.43. So we only have a 43%. When we go this 100%, or like 1 increment in x, we're only going 43% in the vertical direction. And then, so hell yeah, so this red line follows that. And so this is 1, I should have blown this up, but this is -1. And you can see that, you know, at some point, like right in here, let's find our 90. So here's where it hits the wall. Yeah, kind of the halfway point. It's the fastest it's ever going to go up. Nah, I can't say that. Not the fastest, but so like, hey, right in here, look at that. Like with if we get to about here, one increment of x this way, pops it up like almost not 100%, but hell yeah. So that's what that's representing. And I'm glad I'm doing this because I'm constantly wanting to save velocity, but it's not. I'm moving x 100% and I'm getting only like a 70 to 80% increase, like right here in this height. So this height is like 80%, and hey, if this is 1 foot, that's going to be 100%. Move this 100%, this pops up 80, and at some point this goes to 0. Oh, I think this 0 value, so yeah, where this hits 0 is where you get no more juice. Because if you can see, if this gets totally vertical, hey, this thing's not going vertical no more. And once it's at the vertical, hell yeah, you get 0. If you go to the microscopic scale, we're going to move this just a little bit, you don't get anything there. So when this crosses, that's where it hits the wall. So yeah, I got to get better at reading these graphs. But there you go. So this one went. You had so if with 100% move in this, with 100% move in this, we're calling this 100%. Hey, this moved not 100%, but it moved this direction. So we moved 75%. But then at some point, it started moving back the other direction. Back the other direction at like 1, but and then once it's around the 0, it hardly moves. 100% increase, 100% incremental change in this only generates 0 to a small incremental change, but it's going to be in that direction after you pass this sweep. Okay, hell yeah. Now this is going to get, it's going to start at 43%. Essentially, you're going to get a little bit more juice, so when we move this in, this is hardly going to kind of move up 43%, but then, these next couple increments, hell yeah, pop it up. And then from here to here, these next couple increments, you're not getting much juice. And then right at the end, you get no juice at all. So hell yeah, nice reading that graph. But anyway, I think the take-home point is just like, hey, can I look at this equation and see that this is the bx term and this is the cosine ratio. This is going to be the sine ratio. Opposite over hypotenuse. For cosine, it's adjacent over hypotenuse. And that was the aha moment. It's just like, hey, just looking at a bunch of square roots and, like, I think the square roots confuse the hell out of people because just using a sine and cosine is kind of where the teachers, want you to be. But man, Pythagorean's theorem is just so obvious. And, as long as you can figure out that if you're squaring and adding both these terms, so I can just look at this and be like, hey, that's going to be a hypotenuse. Where if I come over here to, I guess we did it right here. So if I want to get this value and I see that we have a, some number minus, it doesn't matter what the size is, you have a number minus another number. Well, for one, two things. This number has to be bigger than that by definition. But if you're taking this squared minus this squared, for sure you're getting another side. This is your hypotenuse. This is one side of the right triangle. Square rooting it gives you the other side. So hell yeah. So this squared minus this squared, square root that gives you that side. Alright, I think I'm done with this one. So I'm happy, and thanks for joining me. That's a video.